welcome back. My name is Joseph. Today we're going to talk about the cooling system of diesel engines. We're going to go over the list I have here and we'll take it piece by piece from there. I've got a lot more interactive a class, I got a lot more diagrams, and I believe this is a lot better setup for me to be able to teach you a wider range and fill out a lot more of the blanks that I haven't been filling out in the past. Because I don't really know the level of expertise of everybody watching these videos, but I feel like if I teach it to you in the entirety that I know it, kind of do a brain dump, then at that point I know I've at least empowered you with more information than a lot of people would get for free. And that's what I'm aiming to do, is give people information that they can use. And sometimes these videos are 45 minutes long. There are 5 people, 5%, 10% want to watch it all the way to completion. Some people drop off halfway. But I know those people who watch it to the very end, they're going to spend their time, and it's going to be a whole lot wiser of an expenditure of your time than looking there scrolling through TikTok. Okay, so what is the cooling system? What does it do? And I scroll too through TikTok. I'm not casting stones. I'm just saying, to be noted. What does it do? It keeps the cooling, the engine to a operating temperature. All right. There's 3 stages that happens in. The first one is warm up from cold start. All right, and then the next is at operating temperatures, thermostats open, and then the third is to manage thermal events throughout operation. So we're going to talk about the Goldilocks zone. All right, this is really, really important to focus on this when you're thinking about cooling systems, because all too often people have swapped all 5 parts in the system, and on the 5th one they're right. But a lot of times I've never needed to pull a radiator to check the flow. Why? Because you can do that with a thermal gun. We're going to go over these things, but this is going to separate the guys who you see later on in your careers, or you heard already, who say you got to pull the this to do that, the radiating cooling package, and send it out and wash it. And you should be able to do that with a thermometer. All right, that's 6 hours labor you don't have to sell. You should do a thermometer. So we're going to get under all this stuff that in these classes will be specific to my experience. So it's not just like I'm teaching you how theory or how things work. A lot of this is particulars, and that's what I think a lot of the people miss out in the latter part of the classes, is that I try to keep particulars all the way through it. So, without further ado, why pressurize the cooling system, and why do we use coolant? The possible causes of overheating, and the possible causes of overheating under load. We talk about drivability and performance on diesel engines, right? So when we pull that hill with no airflow, how does it do? Fluid mixing. Not always the head gasket, guys. It's not always the oil cooler. We're going to go through all the possible causes of cross-contamination, where you have oil interacting with other fluids and gases, or close to interaction, at least in the same vicinity within parts, being separated by gaskets, or we're going to get into all this, but there's many causes of failure. Okay, so we're going to talk about how to test them too. Altitude considerations. Obviously, we have a lower boiling temperature at altitude, so we need to consider that. If we have, coolant, we'll get into that as well. Tools. I did a whole separate video on tools. I'll put that on the very end, and you can check that out. I also put some links there, so you can support the channel if it's something you're interested in, and also have the same kind of tooling that I have that I'm pretty proficient with. Well, really proficient. Troubleshooting the parts. So we'll talk about the Goldilocks. We talk about all the parts inside of a system. We're going to talk about how to troubleshoot each one of them. And then I'm going to give you my personal notes, if I haven't already. So we're going to start off with what it is. It regulates the 3 stages. We talked about that. And the cooling system is essential because major component failure takes place when you don't have a good cooling system, or within 25 degrees of normal operating temperature can cause catastrophic failure from thermal events. So like 262 degrees, maybe not 25, but 262 degrees, I've seen heads crack. So thermal, temperature management is key. We're trying to get every diesel engine to operate from 180 to 220. That's the sweet spot for that peak combustion, the right amount of external temperature to get really good combustion out of the temperature at an exact time. If I heat this cylinder more than it should be, then I can have possibilities of, by the time that air gets squeezed inside the cylinder, it's going to be too hot with fuel and it's going to pre-detonate, right? So I need to keep in mind that engine knocks and these types of things are some of the most drastic catastrophic failures that can happen to engines. You can have block failure, cylinder temperatures obviously high, okay, head gaskets, cylinder walls, pistons, crank and cam can swell. So the exhaust temps that we're pulling these hills with, they go from 7, 9, 12 and up for temperatures, right? In that range, but that's awful hot. So all that exhaust temperature has to be able to get out of the engine, and a lot of it doesn't. So it's retained inside of the iron of the engine, and it needs to be removed through that cold air exchange over the cooling package. Okay, that's when we're getting into managing temperatures. So when we talk about warming up, we're talking about thermostats closed, and I have a diagram here just to show you a cold engine. Get this in view well enough. And right here we have our cooling package, a radiator fan, clearly, a pump. And then I have a pump here for a 7.3. I want to show you this kind of layout because on a 7.3 it's pretty much all in one. So this is a little 4-cylinder diesel, right? So right now we have no flow outside of the block and the pump and the head. It's all right there, circulating, right? So as soon as my thermostat goes from closed to open, I now am circulating into my cooling package, and that is when I'm at operating temperature. And when I exceed a set temperature by the engine fan, then my fan is turned on through this circuit here. So we have a fan hub, like a Horton air-operated fan hub. We have a solenoid here, right? A lot like this one, this fan hub solenoid. Everyone's seen one of those. Now those are controlled by the ECM and a lot of the latter model engines, or the ECM controls relays. Oftentimes those aren't part of the ECM control wiring if they're for RVs and transport vehicles. So see how it's wired, see how it's parameterized inside the engine for fan control. That's key to know that, all right? But what we have here is we have the ECM, and we have there's 100 psi from our tank to our solenoid. So when air is applied, the hub is released, right? And when air is off, it's a fail-safe that when you lose the air, because if you had a solenoid failure or an air leak failure, they still want to be able to operate the engine because critical temperatures, all right? Very, very important. There's more to be said about the stages of how critical, but I'll get into that later. So at operating temperature, we're at 180 to 220 again. So over temp fan operated, we talked about that. So let's talk about the Goldilocks zone. I'm going to talk about, I drew a diagram here. I don't know if it's entirely clear, but you can kind of see what I'm saying just by the illustration vaguely. But I tried to pick a good place that I could get everything in view and do it all in one shot so it could be very succinct. I have a cooling package here, thermostats, ECM with the fan control, and then I have the belts, right, running my water pump. So let's say that it's possible to have a 5 score on each of them, and some of them are limited to a 3 out of 5. That will do it 70% of the time. If I want to bring that to a hill where I have no airflow, I'm pulling that 7 to 9% grade and under full power, meaning I'm pulling my 80,000 pounds, I've got to be able to have max efficiency within the cooling system. So even a thermostat opening a little bit late will change my normal operating temperature, and my engine will constantly be trying to catch up. Or if it closes, if it opens but not all the way, that might not show its face until you pull that hill. Okay. So there's complex engineering involved in making that happen, and we need to keep and maintain that 180 degrees the whole time that we're managing all that temperature. So why pressurized coolant? Obviously it's because it raises the boiling temperature, but it's a considerable amount. It's about 40 degrees. So under 0 psi, it's 212, right, like boiling, and then 16 is 252. We use coolant also to raise the boiling temperature, to condition the steel inside of the engine and the iron and the cast to make sure that it stays corrosion free and that everything is operating freely. Things like thermostats will bind if you get corrosion or additive fallout, dropout rather, and so be mindful of the quality of the coolant. But essentially it's there to raise the boiling temperature and lower the freeze point. So if I go with a 60-40 mix, and I'm under 0 pounds of pressure, the difference between that and water under that 0 pounds is still, it's about it's about 12 degrees. So this matters because obviously I can only manage that kind of a temperature soak into the steel so well. It's going to be very difficult if I didn't have everything operating, especially things like the coolant percentage, because there's a huge drop when I go under pressure. So if I got 16 pounds of pressure on a cooling system and it's a 60-40, I'm not going to boil until 273. Now, if it's the same 60 pounds and it's water, it's going to boil at 252. But it's very likely that your engine temperatures on a hard pull where your fan is on, you should be fan on somewhere around 210 degrees on the Cummins ISX engine. But if you don't have if you have a partially closed thermostat, then you're going to be restricting the flow and the dissipation rates are going to change. And you're going to be running in those 250s, 270s. And before long, you're boiling all the coolant and now there's nothing inside of there to do anything with. And you might mistake this for other things, but that's why coolant quality, I put a whole page into it because even the manufacturers only use specified coolant when they are on different additives or coolant type required because each one requires different levels of foaming, like cavitation can be caused by foaming, right? Because you got it imploding against the cylinder walls and stuff through their wet sleeve engines, so there's coolant running around each cylinder. But if it's got aeration inside of it or it has foam, air, bubbles, they're going to whip into the sides of the cylinder walls and they're going to put little pits in there. And eventually that will pit all the way into through the cylinder wall and you will drop coolant inside of your crankcase. So these are just things that electrolysis, all kinds of scale formation, those types of things. Scale formation on the sides of a cylinder wall, if you get buildup of a scale, right, like a scab of just coolant additives, then what actually happens is it will create a hotter spot on that cylinder wall. And that hotter spot will have a premature failure before the rest of the uniformly cooled cylinder. That one spot that's in a really hot spot, especially if the scale formation builds, it causes cylinder failure. So they put all these things inside the coolant. So I put in the tools some coolant test strips. Definitely use them. If you have bubbles in the coolant, check it for, first off, if it's even boiling, just check it. It's not going to hurt to use some of that block tester fluid, and this will tell you if it changes from blue to green or yellow, green in diesel, yellow in gas, then you know for sure that you're getting combustion gases in there, all right? So that's just really quickly want to say that. So the possible causes of coolant temp. So if we're talking about the gauge reads over hot, right? It could be the gauge. So don't discount the gauge. And we're not going to talk about the gauge as much. We will talk a little bit about it with this temp sensor here I have set up in some test equipment to show you and how it works. But essentially what we're talking about here is if I go to look at the modern gauge, so I've got, these two gauges, right? These are hooked up either in daisy chain to where they're communicating on the data link. So they're reporting the information that is being received by the coolant temp sensor on the engine. And sometimes there'll be a coolant temp sensor that feeds just the gauge on a big semi. You have to be mindful of that because the ECM needs an input. Like a C12 will have one right on the inside there of the front cover of the engine. And then on a Peterbilt, it'll have two on the back right of the block on that little coolant manifold. And it'll have a temp sensor and a sender. One of them might be an alert or alarm stat. One of them might be just for the gauge. The gauge may be 1 to 2 wires, depends on if it reads across the sensor, the resistance, or if it reads resistance to ground. On a 1 wire, that's what it's doing. So don't discard, and I did want to talk about briefly, but don't discard the gauge giving inaccurate information. That's why we always take it from the ECM and the gauge and make sure they both match first. There are some times where customers have told me, like on RVs, where there's different tech applied, but they'll tell you, hey, my temp gauge reads hot. And it doesn't, in fact, overheat. It's telling a lie, and that's because the gauge in that case was bad. But they're smart gauges, meaning they can transmit data. They have processors inside of them, and they can transmit data. And they are usually have resistance values built into them, so that when you plug them in, the computer knows what they are. So, so let's talk about the rest of it. This is the interesting. So coolant mixture, we talked, airflow obstruction, a rag test thrown in front of a charger, cooler, or cooling package, radiator, condenser, whatever, is not a good airflow test. That is not the way to test them. We'll go over how to do that. So fan slipping, fan solenoid pins, wires, controller, ECM. Remember I talked here about any one of these possible causes of failure, all right? That's just the electrical side of it. So let's look at the, well, in a minute I'll go over the air side. So we got temp sensor. Here's a temp sensor right here. Here's another one. All right, the wires and the pins. I told you we have to make sure that that's a verified accurate measurement. So we take a thermal probe or a thermal gun, and we measure right next to the sensor. There may be a few degrees. Make sure you're not doing it with air in a fan on situation. We want to do it just as stale air, as static as air as we can. And it's a pretty good accurate reading if you go close to the temp sensor. As far as thermostats and checking when they're opening, it's more important that you're dropping the temperature degree from the top to the bottom under the load. We'll get into that, but as far as like checking their opening and closing, it is crucial that they open all the way, and it is crucial that you're measuring when they open. Because if it's too late, that's a problem on its own, and it's a simple fix. But don't replace a water pump because the thermostat's not fully opening. Fan, air side, the hub, the hoses, the lines, the fittings, 90 pounds of pressure applied to that hub to release it. All right, and EGR cooler. Now, if my fan is on all the time, can it make an engine run hot? Actually, it can make it run hotter than normal operating temperature, because if I'm pulling a hill, all right, and it's circulating, that's an additional load of 40 horsepower on my engine of driving that fan hub. If that's always on, it's going to depreciate power, which means my gear, RPM, and the sweet spot, the power band, it's going to be a harder time trying to stay in there, which will get you excessive temperatures at higher RPMs. So you got EGR coolers, right? Thermostats. Water pump, very seldom is it a displacement issue. You can see here I have this water pump. Unless that bearing inside there goes, it doesn't really have a way to displace more or less. I have seen I think 2 or 3 pumps where it was slipping on the shaft at really heavy loads. When the fan would come on, it would just pull, all right? And it would yank it, and it would, the impeller in the back and the pulley in the front would slip a little bit. And I don't even know that was really the problem, to be honest. I just know they were able to prove it. I have a water pump will fail, yes, but when they fail, they either weep or they fail, meaning they don't pump. So you have a catastrophic failure to the backside or mechanical part of that, because it's just a 1-for-1 impeller. So what I do find, though, is that it's usually a worn tensioner or a pulley or a belt. Like a C7 will have what you think is a water pump issue, but the belt's just not tight, and it has to be super tight. And if you have a V-belt setup, let's say you have 2 belts sitting next to each other like this, I push down on this one, that belt shouldn't go past that first indentation or a certain amount of foot-pounds, and they have belt tension gauges that will tell you how much foot-pounds of pressure is being applied to that belt. That's really, really important when it comes to cooling things, especially when we're talking about turning that pump. Because if I have slipping on that pump, it's not going to be able to keep up the flow rates to be able to keep that much heat out of the system. Okay, so head gaskets, exhaust into the coolant, happens all the time. 750 degrees, right, just to get ignition. And then, up to 1200 operating. So if that exhaust gas is leaking into my cooling system, it's going to create a high temperature situation. Like I said, put the block tester on there and check for stuff like that. So heads, obviously, fuel filter mixture, too much fuel, right? We can get a lot of temperature out of too much fuel. We talked about that with RPM and the RVs and stuff. Barometric pressure sensor pins, wires, and controllers. We're going to talk about that when we talk about altitude, but barometric pressure is a calculation for fueling at certain altitudes. Also, boost limiting at certain altitudes. So you can get into AFCD rates where it's not going to give you full boost. It may give you a lot of fuel, but it's not, and you'll start to gain temperatures. But it won't do the full boost because that's software written in so that you don't get into a failure of your turbo, overspinning, overspooling. Air thinner, right? So oil low or not cooling. So obviously our oil cooling, we have a cooler where there's some exchange happening there, but we have a lot of iron that's getting a lot of heat put on it. And part of the job of the cooling package is oil. It's just not ever really thought of that way. Let's say you have a lot of windage or aeration in your oil. That can actually go to your bearings as not full oil, and it can overheat and cause thermal fatigue to those bearing materials because it's just not enough cooling capacity with all the air in there, it's relying on it being a solid fluid state around those bearings. And same thing can be said for cooling. So ISX fan on at 210. So we got oil cooler would be something like 240 for spec, 210 for operating temperature, but there would be a 30-degree differential for an oil cooler. Obviously, there's going to be some heat soak exchange there from one to the other. The one that's higher, obviously, is the one that's trying to cool. The cap not holding pressure. So this I see more than you would believe, and I see people pulling. I live in 8,000 elevation, and it gets really cold here. I see a lot of different environments I was not used to. I've been here 10 years. And I have seen a lot of things, very interesting things happen at this type of elevation. Coolant quality is something that I brought up because of that, but cap not holding pressure. So if I go to elevation and I drop the amount of pressure, that means I drop the amount of boiling temperature. And so if I'm 5 pounds off, it might not be a big deal, but if I go to that elevation, it becomes a big deal. Okay, so usually pumps, belts. We want to test all pumps and belts at 1500. And make sure that they're cooling. Let's say you had to check pump pressure. You would check like one of the ports that are constant feed off of the block pressure. So let's say you pulled a heater core and you checked pressure at that line with a low pressure gauge, right? So the whole point, you'd have to run it at 1500 to even check it. You couldn't do that at idle. And that's not how you test pumps. So we've talked about the Goldilocks. Can't say enough about that as far as like things being their best. Overheating, only load, only underload. So we talked about regular. Let's talk about under max load. 120,000 pounds sometimes, guys. So the diag only possible on a dynamometer. So there's some things that you can't simulate the max load unless you're pulling the hill. I talked about in the tools video how you can use this as almost like a laptop / dyno, and some of the tools and tests you can do with that. And I'm going to keep screaming it because if you guys incorporate this, something like this pressure transducer, this multimeter, and this face, you don't need a laptop with the newest software necessarily to interact and see values. Your basically data monitor logger is you, right? As long as you know how to monitor and log, necessarily log, well, some highs and lows maybe, but my point is you can see live data. And live data is the thing. And when I talk about it in the tools, you don't need all the diagnostic software. You need to see live data. You need to see what the computer sees so you can make measurements and tests to make sure that you're all seeing the same thing and that what it's seeing and saying is accurate. It's oftentimes I find coolant temp sensors that will fail in range and run an engine really cold. It still runs, all right? It has more smoke and it runs, but its fuel economy starts to tank because it's running on a cold map versus a hot map. So the way that they map fueling is based on temperature, based on how well it will combust. So this is important to know that you're going to be throwing a lot more fuel down if you're cold. Temp sensor. Transmission stuck in gear. I've seen it. Too high RPM, right? Will get you. Another thing too is I know I've talked about this in some of the other class, but if you have a regen and you're trying to get your exhaust temps up, you can drop a gear, but be mindful of your cooling temps will have to soak up that excess of normal operating temperature. It's not what it's supposed to be. It's 1500 degrees power band. So thermostat's not open just a little bit. I can't say that enough because I've seen thousands and thousands of dollars spent because they say I just replaced the thermostats. That doesn't matter. I need to test everything. If you have a problem standing before me, you can't tell me what you replaced because I see people replace things with bad parts, used parts, and parts that fail quickly. If you're troubleshooting, you never, ever, ever remove a new part from your equation until you've tested it. So I'm going to go over really quickly just to, well, I'll wait until we get to temp sensors. Boost value, not enough. Manual gauge, wireless transfer. So we can look at boost leaks. Low boost can cause more fuel and higher temps. Not because the engine's being derated, just because it already had a leak. But now I'm at altitude and I'm already reading a different amount of pressure based on altitude increase, up to about 5 PSI sometimes when you get to about 10,000 is what it will read as far as inaccuracy for boost temperature or for boost pressure. That's why it cuts you back so that you don't go too much. I hope that makes sense. And if it doesn't, please leave it in the comments and I will make a whole class on it. But it's good. I've seen turbos sheared back to back over a misunderstanding of altitude. And I'm not ashamed to tell you I did it. All right. It was also a tuned engine, and I did not know that. For a lot more boost. So belt tension pulley matters more under max performance. Fan hub slipping under a load. So I have a fan hub friction disc here, and so I have obviously the top where the fan bolts on, and then the back side where the skein is and the mounting pad. And so this is the piece in between. So when the fan goes psh, and the fan comes out, right, and it's released, it should spin freely. When it's engaged, it shouldn't spin at all on the hub. A lot of times what you'll do is you'll turn the key on or turn the key off, and you can grab the hub and pull it. And if you can pull it and it slides, the hub, the one with the fan blade, and it slides over this, then you need to check the thickness of this friction disc on this fan hub, because it might not be a big deal at low RPM under a low pull, but that makes that literally a 3 out of 5 as far as the fan's efficiency when you get to pulling that big hill. And hose. All right. So I'm going to do this next one as a part 2 because I don't want to hold these videos up for too long, and I find myself talking, but I really feel like I'm going to get as detailed as I can until people tell me, hey man, we don't need all that. Then I'm just going to keep doing it because I find to me it would be more helpful. That's about why. Okay, here's video 1 for cooling. Video 2's next. All right, this is a continuation of the cooling system class. We're going to talk about fluid mixing as far as the cooling system goes, and then some of the other fluid systems where you can see some intermixing there too as far as cross-contamination. So as far as coolant in the oil and oil in the coolant, we got to check the oil coolers. We can take something as small as a rubber nozzle and plug on one side of the cooler itself, the tube, and inject regulated air pressure, not beyond system pressure. Usually about 15 pounds is enough to see, and you can tell if those bundles are leaking air pressure just by listening or putting it underwater. The only other thing I've found that to see if you have a busted cooler is there's a test plate kit that they sell, and it's kind of expensive, and it requires compressed air and a few fittings, but essentially it does the same thing. Remember too that oil coolers, any cooler, will split, especially EGR coolers, and I'll talk about that in a second, when there's a huge temperature differential between the fluid going through the tube and the external temperature of the fluid outside of that tube. So there has to be a certain amount of temperature there where it doesn't exceed that, or you'll have those bundles or those tubes will split. Excuse me. Okay, head gaskets, obviously. Compression gases into coolant. Coolant and oil. So head gaskets themselves, obviously you have a coolant passage on the head gasket and one for oil. And if there's a passage between there where you've got your block, one passage here for oil, one passage for coolant, and then the gasket, and then the head, right? If there's allowed any passage between the two of those on the head gasket, then you'll cross-contaminate. That's what I was saying. Cracked head, okay, transmission coolers. They use 50-weight transmission fluid, some of them, and that can be mistaken for an engine oil issue with oil in your coolant. Make sure you don't discount the oil cooler on the transmission. Liners, usually coolant in the oil. Really low pressure. Oil pressures can get up to about 150 operating, and especially cold, and coolant system pressure doesn't exceed 16 psi. And so when we think about that, we think about pressure over pressure. Which one has a leak? When the engine's off and one's under 16 pounds, that's when it leaks in. But when it's running, it might be at a spot on the cylinder liner that it pushes compression gas into, or likewise. So be mindful, there is some interaction, but usually what you'll see is the lower pressure is the one that loses. Okay, so you'll have whatever higher pressure contaminating into that lower pressure. Water pumps, all right, can create coolant in the pan. So you pull the pan, and same thing with liners. You pull the pan before you pressure check, all right? So we pull the pan, look underneath there with the flashlight. You can usually see them weeping back into the front cover in the gear train, all right? Because usually big water pumps are tied into the gear train in the front cover drive. So cracked block, turbo if coolant goes into it, and transmission, right? We talked about that. So let's talk about air into the coolant system. It can happen where you have pneumatic, like compressed air coming from the air primary, secondary, auxiliary system. On some Freightliners, I know they have a heater control valve that will leak air, and it looks like, but it won't test positive on the NOx tester or the block tester, right? So don't discount that there's a heater control valve that has some interaction where there could be air getting into the coolant. That is not common. Fuel in the coolant and coolant in the fuel. So I told you a minute ago, 16 pounds versus 300 sometimes, all right? Exceeding that sometimes. So the fuel cooler, some of the lighter duty engines use a fuel being cooled and using cold air to do it. So keep in mind that there's interactions in different places where you have coolant and fuel, and they can crack, especially those little remote coolers. They crack. I think they even did away with that and did a rework, but the point is, wherever anything interacts, don't discard it. The injector cups, the dosing valve, the fuel cooler, the fuel pump, if coolant goes into it. Sample the fuel tank and let it sit in a container that is completely clean, no water, blow it out with a nozzle, set it down and let it see if it separates. You won't see those bubbles quite clearly until you let it separate. And like I said, if that happens and you have coolant and fuel, you have got to get rid of all the fuel in the tanks. If you sample them, get one of those little siphon things and get from the very bottom of the tank, because that's where it will settle. Fuel in the coolant. So transmission fluid in the coolant. Auto radiator cooler. Automotive applications, light duty, you'll see sometimes that interaction there. That can be in the cooler. Exhaust in the coolant. Talked about that. Altitude. Got 3 more pages. Coolant mix matters. Okay, so at 0 elevation, water boils at 212. At 8,000, water boils at 197 degrees. That's a 15-degree difference. So with coolant, at 33%, it equals a 260-degree boiling point at 16 psi. At a coolant of 0, it's 252 at 16 psi. And you want to maintain temperatures in your coolant that are about 25 degrees plus or minus Fahrenheit above and below operating temperatures with your coolant rating, all right, as far as your mixture goes. So I want to talk quickly about atmospheric and barometric inputs. Atmospheric pressure is obviously different at altitude, all right? So at 0 altitude, it should be about 15. Now, we're talking about atmosphere here. It's different than baro, all right? Barometric pressure is usually about double whatever atmospheric is. And what is key here is that if you're looking at that value on your computer, you want to make sure that your atmospheric pressure or barometric pressure is reading within the right altitude range, because like I said, there can be fuel issues. So at 0 altitude, it should be about 15, plus or minus 0.50. And at 8,000, it should be about 11. That's just some quick references for you. At 10,000, it's seldom under 9, but it can be, all right? Go all the way down to 8. So on barometric, at 0 altitude, it's 29.2 or 29.92, and at 10,000, it's 20.60. All right, so a couple of numbers throughout there. Hopefully that helps you in your notes. Boost foolers and tuners beware. All right, I talked about that, but if you have something tuned for boost and you get it at altitude, you're already lying to your engine, and it's already going to make a lie for itself if it has barometric pressure that it's too high to spool your turbo. Okay. Troubleshooting tools. I'm not going to talk about the tools. I will talk about AC inputs for like air conditioner, because that will cycle your fan. You can also get the same thing for intake temperatures will cycle your fan. And so if you have a fan that's continuing to run, you want to make sure you know why, right? Engine braking now, we can have fans turned on, because why? Because that 40 horsepower robs the power, slows everything down, and then we have what? We have turbos maxing out in third stage braking all of the air pressure density that they can, smashing it into that cylinder and making it a very good shock absorber. So everything in engine braking might use some systems in the engine to assist. So don't discount that. Okay, so now we're going to get into overheating troubleshooting. This has 2 pages, I guess, and then my notes. The 2 pages, this might be the most important part because obviously we talk about a system. I want you to know, I want you to be able to, I want to teach you what I know about how to troubleshoot the pumps, the cooling package, the pressure cap, the thermostats. Let's just start here. Okay, so the pump. So we checked the belt tension, right? We talked about that. Overheating at idle is a generally, you will have this symptom of overheating at idle, or when I stop, it starts to overheat. A lot of times that's because the airflow assists in cooling the engine, but when there is no airflow, it's dependent upon the pump circulating that coolant and dissipation of heat through the cooling package. So no flow. So we check the pump discharge from the heater core, check the pressure system. 15 psi is the spec on the system of the pump, or the pump and the system. So I think that covers what I had to say about water pumps. I do want to take a moment to take a look at this water pump, and just to show you that its passages are sealed off here by different gaskets. There's one port here and then one big port here. So all the coolant in here is the one that's flowing through the block, right? And then now there's coolant under here, but it stays here and in the block until it reaches temperature. When it opens, this thermostat opens, then coolant starts to circulate out. And then it's in a constant loop. All the coolant is in that loop. So it has flow all the time, but if you were to check like a radiator by pulling the cap off and checking for flow on a cold engine, it wouldn't tell you anything because there's no flow external to the block. So keep that in mind. So the cooling package I want to talk about really quickly because it's important to me that we understand it's very easy to test one. Very easy to test one. You do it with a thermal gun, you do it with the fan on, and you do it with in a thermal event. You want to see how well, if I push hot coolant into this engine at 220 degrees, it's supposed to come back 40 degrees less. That's an engineering spec. Every fan's supposed to do this. This is the way it's all built, okay? Don't let anyone tell you they need to pull your fan because they think it's plugged. Ask them what the temperature drop is from the top to the bottom. Under load even, you can do it, and I'll show you how. Same tool I show in the tools. You put this on the upper, the inlet to the radiator, or one of the back side, you go to one of the top of the vanes. You just plug it in there, or just poke it in. It's not going to pierce a hole in anything. It's not going to hurt anything. And then you zip tie that in place. You get this screen, and you go pull that hill. All right, now I know what it comes into the radiator at when I'm pulling that hill. Now I stop at the top of the hill. I put that thermal probe on the bottom, right? That's what's coming back into my engine. And then I pull that same hill. There, if you have a dyno, you can do this, but if you don't, this is still possible to get it done. And then you see, is that a 40-degree drop from the top to the bottom? And if it is not, then the radiator's plugged. And it might not be the radiator, it might be the condenser, it might be the charger cooler, it might be anything stacked in front of that cooling package can restrict airflow, and therefore it cannot achieve that 40-degree drop from top to bottom. And that is how you check them. And I've told people that, and I've learned this in engine schools, and you know, I wish people would just say, and I got quit telling people I got to spend $600 of your money when you can do it with a thermometer. I'm kind of ranting on that one, but it's kind of a pet peeve, so to speak. Also, the slipping fan, don't discard that. I told you there's a tool actually that they make when they sell the kits to check the friction disc thickness, and it just looks like a little half moon crescent, and it goes in there when it's released, and if it fits easily, then it's too loose. It's supposed to fit kind of snug, because after that space is gone, those two need to lock together. And be very careful if you're rebuilding those hubs to be very safe about it, because the spring that's compressed in there goes from about that big to about that big, and it'll unhinge your jaw. Okay, pressure cap. Obviously, we're just going to do, I have my stance pressure tester, good old tried and true. Got my collar, I put my cap on, and I lock it into place. A lot of times, Don't discard that the radiator neck inside of the reservoir has damage to the seat. And if it's pitted and whatnot, you can put like a wire brush in there and clean that up. But don't expect a rubber seal to seat against a pitted surface. It can't. It's going to leak out and you're going to drop pressure. It might hold 10 pounds, but not 15. All right, that matters. That matters a lot because most people, guys, it's like 15 bucks tops for a radiator cap for the most part. And you always want to start somewhere that's simple. And if you don't have a pressure tester, buy a cap. Okay. Wait, got a backside. So when we talk about the fans, I'm going to say separate the problem of the fans. So these fans, like I said, operate on this ECM controlling one side, and then the other side is controlled by air. So I have to make sure that I have the applied air that I need to the solenoid, right? And then I need to make sure that when I operate the solenoid, that that some of them are normally closed, some of them are normally open. They are all wired different, but air pressure releases, right? So normally closed one, normally open will operate in reverse of the other. So know what it is you're working on. Cat, Detroit, they all seem to find their own way about it. But what I want to make sure of is that at the hub, I have 90 pounds. So all I need to do is get an air pressure gauge, something like that, all right? And I need to plumb that into the air line that goes to the fan hub, and when I apply it, I want to make sure I got my 90 pounds there. I need to start there every time. Too many problems created because you'll put a new fan hub on, and it'll slip again because it has leaks. And they'll be through 2 or 3 of those fan hubs, or a catastrophic failure in a fan hub because it's not being released all the way, and it's building a lot of heat when it's slipping, and it'll melt the bearings on the skein itself. Like I said, it's a very high load on that fan hub. Something you want to make sure is that it has all the things it needs going to it. And I talked about on the tools video, but I'll mention it now. If I'm checking this solenoid, I can unplug the solenoid and apply a small load that's relative to the amount of load on that solenoid. Not a 15 amp load, because I'm running that 15 amp load draw on that computer, and that can burn out the computer, and it can cause problems with it that aren't even there because you're asking for too much power out. It knows how many amps are supposed to be drawn, but it does. I would recommend using something like a load because then you can verify the wiring and the driver inside of the ECM. And you can't do that without that load being applied. Fan solenoid will take out the ECM if they go bad. So you want to map the circuit. Make sure you know what you're talking about. There could be a 12 volts there. It could be a ground being provided by the ECM. The reason I told you to separate them is because what I do is I take and I put my blowgun here that I showed you. I'll put the right fitting on it, and then I'll just keep constant air. And then I want to make sure that that side works. And then on the other side, I do it with the test light. By separating that by, is it air or is it this? It's a really quick way. If you try to incorporate it all, sometimes it becomes overwhelming. A hydraulic solenoid valve to operate hydraulic cooling fans on things like transit buses is used, and that's usually hardwired within the transit bus itself. Those aren't always outputs from the ECM. Sometimes they are. Amp draw, so I can do an amp draw to the solenoid itself is another quick way. I can put my amp clamp over the wire and see how many amps it's pulling, if it's pulling any at all, right, to tell if it's operating or if it's pulling too much. Also, resistance checks across them, just putting your multimeter in your ohm readings and testing the coil by putting one lead here and one lead here, and it should be within a certain amount of resistance. Check your specs as far as what that is. Viscous fans. I want to talk about them because there are some applications where they use them, but a viscous fan is a fan that bases its amount of drag on the pulley. So either it will drag slowly on the hub, or it will drag really freely. You guys know on light duty pickups there's a lot of applications where you can go up to the fan hub and you can pull it, and if it just spins freely, it's usually on a cold engine. To check it when it's hot, to get the engine warm, and then spin it again. There should be a lot more drag the second time around because there inside of that fan hub is a little thermal probe, and it varies the amount of spring pressure inside of the hub, creating that amount of drag. So that changes based on temperature, and that's not air actuated or anything else. So keep in mind that's the way that some are driven. Now, they have a thermal probe, but also a motor. So like I said, there's so many ways to run a fan. You really do have to know how is this fan ran instead of just going, okay, they're all done the same. Look at your specs and see, okay, is this fan shut off with the solenoid on? Is the air normally going through it? Is it a normally open solenoid? Is it normally closed? These types of things you cannot troubleshoot unless you know. I talk a lot about electrical and I talk a lot about mapping circuits for that reason. Okay, oil coolers. Like I said, we were looking for about 7 to 25 degrees between one fluid and the next. We can look at oil temp and coolant temp on our laptop or however we're doing that, and they should be within about 25 degrees. There's can be a little bit more. I know, like I said, big trucks, it's a little bit more. On some engines, they only allow about 7 to 11 degrees, and if it exceeds that, then you need to replace the cooler. So look at your manufacturer spec for when to replace as far as the temperature differential. Okay. So EGR coolers, we talked about those as far as those bundles needing to be filled with coolant as opposed to air voids. And that's why we fill them with a vacuum. Okay. And I'm just telling you, if you don't do that, you're bound to have premature failure because any air bubbles will create, if they fall on the seam, because those bundles are folded and then basically fused. And when they split, they always split down the seam. And when you see that, it's always because of air bubbles trapped in there. And there's been a lot of failure analysis that gone into EGR coolers for a lot of engines and the reasons why they fail. And they found that it's because of trapped air largely. And that's an install problem. That's on the guy who puts it together knowing his shit. And it can cause overheating if, let's say, you have big, huge air pockets on the cylinder walls. Some engines, they're better just to fill them at an angle to make sure that you, as the fluid comes up, it comes up like this rather than like this and traps a bunch of air. Remember, there's a degas, bleeder, whatever you want to call it, but there's only a little bit of air bubbles allowed to pass through that small hole in the thermostat for all of the air trapped inside the block and everything else. The only way the air can get out to the top, right, is through, that's why we vacuum. And we hold a vacuum until we can get it all out, and then after we fill it up past the engine block, we can re-vacuum several times with this tool and then fill it all the way to the top to capacity. And that's when you know that you don't have any air inside of there. I put that as far as like at EGR coolers, I told you how to test them. We're testing the bundles, right? So you're plugging one side, you can use your finger and a couple pounds of air. You can always hear them leak. On one side of the bundle, you go to the other and you can hold it and put it underwater. You can see it bubbling out. It's quite clear. Temp sensor inputs and fan inputs. So intake manifold temp, ECM for coolant, for fan control. Sometime around 210, a lot of these fans kick in. Some of them is later, it's 216. Some of them, the modern engines do run a little bit hotter. When I talked about 180 to 220, sometimes there is a little bit hotter operating temperature. And sometimes you'll see that in specific modern engines that you wouldn't see on the older ones, and it might make you concerned. But always check your fan cut-in specs for your time, for your temperature that it's supposed to cut in. So, coolant temp sensor, we can verify that. I'm going to show you how to do that with this cool tool. This is just a pot with a heating element, right? This is a 200 watt heating element. So in the field, I always have my portable power station with me, this tool here. All right, so it just has, it's I think 1800 watt average. Anyway, you just plug inside your heater to it and you turn it on and it will boil the water in here. The reason I've made a video about not heating up thermostats with a torch was because you're trying to see if it opens at 190, but you're putting 700 degrees on it. That's not going to tell you anything. So with a temp sensor especially, you never want to heat that thing up with a torch, all right? Because it'll burn out the little element inside of there or the inner workings of that sensor. It's supposed to operate in 220 to 260, maybe 300 degrees tops. At that point, your engine's shutting down, right? So I put some water in here, and then I have my temperature, my thermal probe. And then I have my leads. My leads go into my multimeter, and I put it in the ohms. All right, so as I boil the water, because that sensor is submerged in the water, and then I take my test clips here and jump it to the pins, I can measure the temperature and then I can tell you the resistance. There's a chart on every single sensor that's ever been made where this much temperature equals this much resistance, and it has to match, and it has to do it slowly and measure each little bit of resistance. That's how the computer knows. If that drops off, the computer will throw faults for that temp sensor not reading accurately, or giving 3 or 4 type fault codes for FMIs. The other thing I was going to tell you is I use this also for testing thermostats. So I just set the thermostat in the thing and I heat it up, and I can see as it travels if it's going from hot to cold, and I need to make sure that I can verify that happens at the correct opening temperature. This one opens at 190, right? And it's stamped usually on the thermostats, or find out the spec. But you submerge it and slowly heat the temperature, and then at 190 exactly, that sucker should be fully open. All right. If it's not, that's a problem, because it will affect the normal operating temperature of the engine depending upon when that thing opens. Okay. Oil level and quality. Like I said, don't discount that. Okay, just one last little bit of notes, and then I think we're done, man. So right now I have, get this trash out of there, sit back here, and I'll just give you my notes from behind the desk. So electrolysis, right? If we want to ground the radiator, we don't want to discount that the old steel radiator tanks have to be grounded. Always vacuum refill, we talked about that. So heater core, steam in the cab is a good way to diagnose that, because you can see the inside the windshield's fogging up, and there's a lot of condensation inside of the air, humidity. Oftentimes coolant smells really sweet when you atomize it too, or even when it's burnt. So solenoid for the fan, air can fail intermittent and damage the driver. So each time the computer is operating that fan, it can fail one time and have a problem, and then the next time it goes to energize it, it's in a different, maybe it's hotter or colder, and it won't fail. So that I've seen cause a lot of intermittent failures, that fan solenoid control in the ECM. And there is an ECM test in like Cummins Insight that allows you to operate the fan solenoid on and off with the click of a button. So the fault codes, I want to say this, that fault codes mild, moderate, and severe are logged each in different temperature ranges. Obviously, the most severe might come with an engine derate or shutdown, but and then depending upon how the engine's programmed, it might even have an issue if it sees any kind of excessive temperature. So don't discount, though, if you start seeing the most severe level, that either you had a catastrophic failure, or that their ECMs can lie and tell you that it just registered most severe, and it can be wrong. I've seen that. Leaks or weeps. So C15, they weep, right? They have a weep hole on the coolant pump, on the water pump. Now, if the bearing failure, if the bearing or seal fail inside of the water pump, it will leak out of the weep hole. Usually it's the seal that causes that, but that's a condemned water pump, right? No. It has to form a pool on the ground for them to condemn it under warranty for a C15, or it had to. The point I'm trying to make here is that lubricates that ceramic seal inside of that water pump with coolant. And so on the back side of that pump, it will discharge a little bit of coolant. A little bit of weeping is probably not the biggest deal on some, but check to see, because you never know if the manufacturer had actually intended for that coolant to lubricate that seal, and that's why it shows itself as weepage out of the weep hole. So pressure over pressure, we talked about that already. DPF saturated with coolant. I have brought DPFs back, but you have to wash them out really well, and then rinse them, and then you bake them, and then you check the restriction across them again. So don't automatically condemn something because it's had coolant on it. If it's, especially if it's like wet, like a major failure, if it's saturated, wet. If it's been dripping coolant on it for a long time, those portion of the cells of that DPF may not be good. Let's see. Failed cap will usually hold some. So when caps fail you, they usually hold some, right? So they have a pressure relief valve in there that that is supposed to relieve pressure beyond a certain amount of pounds. It can also relieve pressure at a lower amount of poundage if it's failed. So I can't say that enough, and I know that might make people turned off that I keep saying some things, but I'm trying to drill some things home in particular. And the cap, dude, I've probably seen $100,000 spent in parts over shit that was a cap. And over my years of 2 decades plus, almost 25 years now, I'm telling you, damn near way more than people think it's the cap or the thermostat. That doesn't mean you just throw a cap and a thermostat at it, but if you're going to throw anything, throw cheap ass, inexpensive parts. Not cheap ones, but they're inexpensive before you start replacing $900 fan hubs and thousands of dollars in radiator labor. Heads crack at 260. I told you that. Air can leak and can cause heat. Oh, intake air leaks. I talked about that. 100%. Airflow over cooling package is paramount. Yep. Coolant dam. So you can make one of your own. You can make a coolant dam out of and all that is something that pulls a vacuum on your coolant system all the time, so that you can change parts that are like coolant hoses up to maybe like 1.5 inches, sometimes a little bit bigger depending upon the vacuum. But you can use a small shop vac and just regulate the amount of vacuum that's being pulled, and it will do the same job. But they sell that through Cummins because there's a lot of coolant, right? So the reason why I always, when I put coolant in, I put it in under a vacuum, but I let it hold the vacuum first to make sure I don't have to redrain my coolant to make a repair or tighten something or a seal. Something went bad, right? Because we always check our work. So I'm always going to go after I fill it up, and I'm going to repressurize it and make sure it holds too. But it's easier sometimes to check it before you fill it. I used to do it with air pressure and soap shit, but that's not necessary. Ambient temp. There's only so much exchange available from the laws of thermodynamics and that exchange that's possible, that thermal exchange, from the ambient temp around. So if there's no airflow around and I'm sitting at a stop sign, it might not mean that my engine's overheating. It might mean that there's no way that a good example of this is in air conditioning. I can only drop, I think it's like 40 degrees below ambient temp. So if the outside temperature is 115 degrees, I'm never going to be blowing 30-degree cold air out of that, because the condenser can't change over that amount of thermal exchange with that kind of ambient air. It has to be colder air that I throw over that thing. Same thing with radiators. Keep that in mind on hot days driving through Arizona. It might not be much wrong at all, but it might be a symptom of something not operating at its optimal performance. So, pump impeller slipping, we talked about that. Engine runs cold. Usually the fan is on all the time, or the thermostats are stuck open, right? It's not ever allowing that engine to achieve operating temperature because it's just continuously cooling all of that coolant. And until it gets to that 180, I'm not going to get good fuel, right? Good fuel mileage. Okay. I think that's it that I have to say about, cooling systems. I will say, as far as when it's open, I do want to give you just one last display here. So now I have, earlier I showed you when I have it all trapped inside the engine, right? So it's just circulating. And then the temp sensor, all right, is for fan control. My thermostat is closed and I have no flow. This is stagnant, dead water. There will still be flow in the pump, right? And then there will also be flow to an auxiliary, like heater core, EGR coolers and stuff. As soon as this thermostat gets to a certain amount of operating temperature, now I have flow out. This is the biggest thing I can teach you about a cooling system, because you have to look at it in 3 stages. Warm up, operating temperature, and managing thermal events. All right, guys, I hope these classes are useful. Let me know in the comments if they are. You click like, I keep making them. Sometimes I get a little bit down because the likes are down. So if you can keep those likes up, man, that keeps the spirits up and keeps me driving on that I'm doing something worthwhile. All right, take care, guys.